Number 29. While exercising in a fitness center, a man lies face down on a bench and lifts a weight with one lower leg by contracting the muscles in the back of the upper leg, aka the hamstrings. Letter A. Find the angular acceleration produced given the mass lifted is 10 kilograms at a distance of 28 centimeters from the knee joint. The moment of inertia of the lower leg is 0.9 kilogram meters squared. The muscle force is 1500 newtons. And its effective perpendicular lever arm is 3 centimeters. All right. So we have a couple of things going on in the problem. Here is my Picasso. Here's a man. This will represent his knee joint, and these are his lower legs. I think it said that he's lifting the weight with one lower leg. So I drew two in the picture, but I only attached the weight to one of them, so that should be fine. So it's only this leg that's going to rotate. All right, as it rotates, it'll have some angular velocity. It'll also rotate with some angular acceleration as well. That's what the question's asking us to find, the angular acceleration. So let me just write that over here. Angular acceleration is question mark, okay? Now, we have two things going on in the problem. In terms of weights that are rotating around a fixed point, okay? There are two weights. One weight is going to be the weight of the lower leg itself. Pretend there was no external weight attached. And the man was lying here. Here's the knee joint. Here is the lower leg, right, the tibia. And it rotates then about the knee joint. There is some weight to the leg. Okay, so this leg will have a moment of inertia. Also, now since there is a weight attached to the leg, there is also a moment of inertia, for this particular weight also. So that being the case, right, when we consider then what are the moments of inertia in the problem, we want to think about these two things separately, okay? There's really two moments of inertia that then will comprise the total system moment of inertia, the moment for the lower leg and the moment for the weight itself. Now, if we're asked to find then alpha, okay, the angular acceleration, you start thinking in terms of formulas, and somehow we have to find alpha given some of the information that we know. Okay, the weights, we know moment of inertias, we have forces and perpendicular lever arms. This all should be sounding quite familiar to you, right? Torque. All right, there are torques in the problem. Now, that helps us then define what formula most likely we'll be using. Once I understand that the nature of the question or the problem involves torques, I know then to look at this particular formula. So let's start with that. So this is letter A. So I realize that the sum of the torques is equal to the moment of inertia, the total system moment of inertia, multiplied by the angular acceleration. Now this is easy in terms of algebra, right? To solve for the angular acceleration, this is pretty straightforward. It's just the sum of all the torques, the sum of all the torques in the problem, all divided then by the total system moment of inertia. Okay, so first thing is that, right, in order to solve for angular acceleration, we need to know these two things. Now we have pieces of each, and we just have to further investigate these two parts. So let's think about it. What are the torques in the problem? Well, there's really two torques, okay? The two torques in the problem will be one, coming from the weight that is attached to the lower leg. Okay, that's going to produce a torque. Why? Because this block has a certain mass, therefore gravity is pulling on it, and therefore it has a certain weight. This weight is acting at a perpendicular distance relative to the axis of rotation, angle axis AA. All right. So that being the case, we realize that we do have a torque here for the weight. Also, there is a torque produced by the hamstrings themselves. And it says that the hamstrings produce 1,500 newtons worth of force, and the perpendicular lever arm for those hamstrings is going to be 0.03 meters. So I realize that since there are two torques in the problem, I'm going to expand that numerator. So now we have the torque being produced by the weight plus the torque being produced by the muscle. Okay. Now, it's going to be important to consider signs, but the signs here will tell you, they'll give you direction, okay? Whether it's negative or positive overall, it's totally dependent upon how I frame the problem. All right, meaning I could have just taken the mirror image of this, or those of you who have taken chemistry, the enantiomer, and if that were the case, then his legs would be rotating now in a counterclockwise position as opposed to a clockwise position. So the magnitude of the signs would change, but the sign should change, but the magnitude should stay the same. So then divided by the total moment of inertia, remember, was the moment of inertia, we'll say, for the weight itself, plus then the moment of inertia for the lower leg. Okay? That looks like an E, but it's an L. Now, let's expand on each of those. So now the torque produced by the weight is going to be the force of the weight, right? That's just the weight, okay? This is just W. Multiply then the perpendicular lever arm of the weight, plus the force produced by the muscle, multiplied by the perpendicular lever arm of the muscle. Now, let's just consider what the signs of these two things should be at this particular stage. This weight is applied to the lower leg, and this weight would cause a counterclockwise rotation, and therefore this torque should be positive. Conversely, the hamstring is going to be attached right all the way, somewhere around, I didn't show his full anatomy here, but the hamstring would now be pulling the leg on, or rotating the leg, I should say, in the clockwise direction. And therefore, this particular torque that the muscle is producing should be negative. Okay? So I can put a little negative sign here if I wanted, or I can just simply, put the negative sign here. Then, divided now by the moment of inertia for the weight itself. Now, here's the part of the problem. When you have to think about moment of inertia for the weight, you might be saying, well, I go back to the page in the textbook and I don't see something that looks like this. Well, you have to consider the nature of what shape this weight would produce if it were to rotate about the fixed axis. Okay, meaning about the knee joint in this problem. So you would simplify this weight, okay, down to essentially a point mass located right here on the lower leg. And if this point mass were to rotate about this knee joint right here, it would produce a figure that looks like this, right? Which is hollow in the middle. There is no mass in the middle of this circular arc. The mass is located all along the periphery, okay? That being the case, the best approximation now for that is going to be the hoop about the cylinder axis, where the axis is down the middle. Okay, this will represent the knee joint right here. Here's the weight then on the exterior, and it's rotating around the center axis. So this would be the best approximation for the moment of inertia for the weight. Okay, so now instead of writing the moment of inertia for the weight, I'm going to write the mass, that mass, right, of the weight, the mass of 10 kilograms. I'm saying the mass of the weight. Or the mass component, I should say, of the weight, multiplied then by the radius, which is just the perpendicular lever arm from the location where the weight is to the knee joint, okay? So this is just, I'll just leave it, I'll just write perpendicular because it's the same thing as this thing, okay, of the weight. And then add to that, now these are not, there's no negative and positive down here, they're just the sum. All right, direction is not important in terms of moment of inertia. So now the moment of inertia of the lower leg, oh, thank goodness they gave it to us, right? That was the 0.9. So this is plus 0.9, okay? That's actually, let me just leave it out for now. I'll leave it IL. Now I'm going to plug in the numbers. So this is the formula, and we actually know all of the terms. And if we know all of the terms, we can fortunately solve, right? So I can also expand on this, the force due to the weight, which is just mg, right, of the weight itself. So that'll be 10 kilograms multiplied by 9.8, multiplied by that perpendicular lever arm of 0.28, minus then the force that the muscle produces, which they told us was 1,500 newtons, multiplied then by the perpendicular lever arm of 0.03. Okay, and now divide this whole thing by, we got, I just realized as I'm looking down here, guys, I forgot the square. I'm circling down here. I forgot this is r squared down there. Please don't forget that. And now we have the mass, which is the 10 kilograms multiplied by the perpendicular lever arm again. So this is 0.28 squared plus then the moment of inertia for the lower leg, which was 0.9. And now it's just a matter of calculating. Okay. So as you can see, the math isn't hard. It's just understanding what to plug in, how to do your substitutions. That's where the sticking point generally is. So 10 times 9.8 times 0.28 minus now 1500 times 0.03. And then we're going to take that value, divide it now by parenthesis 10 times 0.028 squared plus 0.9. And we get a value, and it's negative, okay, in terms of how I frame the problem, just because the acceleration will be going clockwise. So that should be expected. So in terms of the way I frame the problem, the answer is negative 19.3, and that's radians per second squared. However, I would just get rid of I would just give the magnitude here, all right, which is just the absolute value, so it's 19.3 radians per second squared. Okay, done. Now letter B. So how much work is done if the leg rotates through an angle of 20 degrees at with a constant force exerted by the muscle? All right, so let's put letter B on over here. Now it wants to know work. Okay, so if you're thinking in terms of this chapter work, and we're talking about rotational work, there is this formula over here on the right-hand side. This says that the rotational work done is going to be equal to the torque multiplied by the angular displacement. Now, in terms of the torque here, it's very important to know what torque, or what I should say is it's really important to know what type of work you're trying to solve for. The type of work you're trying to solve for will determine what torque you're going to use, okay? So specifically, the question is asking how much work is done. Now, are they saying how much work is done by the weight? They're saying how much work is done by the hamstrings? Or are they just saying how much work is done? Well, obviously they're saying how much work is done, which means it's basically, if you interpret this carefully, it means net work. Okay? So really they want to know the net work done, the network of rotation. Now, if I want to find network, then I better know my net torque. Okay? Multiplied by the angular displacement. If I wanted to find the work done by the muscle, then I would find the torque produced by the muscle, okay? There's consistency here in these formulas, and we've talked about that concept a bunch of times. Right? It's very, very important. My theta looks kind of terrible here, huh? Theta. So remember, net torque is basically just another word for, or net here is just another word for summation, okay? So I'll leave it like this. So the net work is equal to the sum of all the torques multiplied by theta. The reason why I'm doing this is because I want to connect this idea to what we did over here. Okay, it's the net torque. So what was the net torque, right, in part A? The net torque was the numerator, right? The numerator the whole time, okay? That's the net torque right there in terms of its values. All right, I'm not going to derive it again because we did it already. So this is now basically going to be the net work will equal this whole numerator value. I'll plug it in. So 10 times 9.8 times 0.28 minus 1500 times 0.03. Okay. Then this whole net torque is going to be multiplied by the angular displacement. They said 20 degrees. Okay. So if you're thinking about, here's a coordinate system. That's terrible. Here's a coordinate system. The lower leg, let's just say, starts here, and eventually it's going to rotate 20 degrees. Okay, so the angle, I don't know why the leg is curling, as that's quite an issue there. It's going to curl 20 degrees, okay, from where it started. So now remember, we don't like to know, it's important to know degrees, but in terms of what we're actually going to plug into our formula here, it has to be in terms of radians. So your job is to convert 20 degrees into radians, all right? So basically what you'd want to do is think about 20 degrees is how many revolutions, and then convert from revolutions into radians, okay? So it'd be a setup just like this. So we would have something like 20 degrees, and we realize that there are 360 degrees in one revolution. So that gets rid of the unit of degree, right? So then I can then realize that for every one revolution, it's 2 pi radians. And look, there's the conversion, okay? Basically, you take your 20, multiply it by 2 pi, divide it by 360, okay? That's what I'm going to put down here on the right-hand side. So it's going to be 20 times 2 pi, all divided by 360. And we will then arrive at our answer. So the network done is going to be 10 times 9.8 times 0.28 minus 1500 times 0.03. Okay, great. And then multiply that now by 20 times 2 pi divided by 360. Great. So now the answer, as you'll see, it'll come out negative. I should have been a little more careful in terms of the signs over here for the angle, right? I'm measuring 20 degrees moving in a clockwise direction. So technically this should be negative 20 degrees, all right, as I'm looking up here. So I'm plugging in the negative. The reason why I know the work has to come out to be positive here. It's not a negative work, all right? The system's not losing energy. There's energy being put into the system. So I know it has to be positive, but it should work out positive. You just gotta be careful with the signs, all right? In any case, the magnitude, and you can always just simplify it by just taking the magnitude at the end. So this is 6.13 or so, 6.13. And here we have the joules, right? This is going to be in terms of joules. Great. All right, guys, thank you so very much for tuning in. I do hope this video helped. Please remember to subscribe, give us a hand, and look forward to helping you with the next question. Take care.